This conference will now be recorded.
Hello everyone. So two chemical properties are left for group 2 elements. Once we finish that, next we'll discuss applications of these group 2 elements and then different types of compounds. For example, hydroxides, halides, oxides of group 2 elements. What are their characteristics? We will discuss that in detail, and if time permits, we can also discuss some problems. So chemical properties, some chemical properties already done under group 2 elements. Now some more properties we will see. So reducing character. So as they are metals, obviously there will be some reducing character. But if we compare with alkali metals, that is group 1. So this is group 1 alkaline earth metals, this is group 2. So when we compare reducing character between group 1 and group 2, it is true that they are also good reducing agent. But the reducing capacity compared to the alkali metals, that is the group 1 elements, obviously now it is less, and that is expected also, because if you consider alkali metals, they are more electropositive, their metallic character is high, so reducing capacity is also high. So both group 1 and group 2 reducing character is present, but if we compare, then group 1 its reducing character is greater than group 2. So this is the order. So this reducing character of alkaline earth metals, now within group, how it changes. We have already compared group 1 and group 2, the reducing character. But now just focus on the group as we are moving down the group. When we move down the group, starting from beryllium up to barium, reducing character increases. Again, that is according to our expectation, because when you move down, metallic character is increasing, and when metallic character is increasing, that means reducing character will also increase. You can also consider it from the that is explanation if you want to give in terms of ionization enthalpy. Down the group we know it decreases, so you can easily remove the electron, so it can easily feed electron to some other species. That is actually the reducing character, right? So ionization enthalpy decreases and electrode potential become more and more negative down the group, starting from beryllium up to barium. So final conclusion when we draw about the reducing character, obviously the electrode potential values helps us. So more negativities, more will be the reducing capacity. But what are the actual reasons? One of the reason is ionization enthalpy decreases down the group, so it will be easier for the elements to reduce other species when you are moving from beryllium to barium. So compared to group 1, their reducing character is less, and when you are moving down the group, reducing character is increasing. Okay. Next is how they behave in liquid ammonia. So we have seen in liquid ammonia how the group 1 elements, that is alkali metals, how they behave. Now here also you can expect the same kind of behavior. So like alkali metals, they also form this type of ammonia solvated cations and electrons. So ammonia solvated cation means, suppose you consider any group 2 elements. I am writing in general M2 plus cation. So when it is losing 2 electron, it will be converted to M2 plus and 2 electron. That is, this is metal, and when it is losing 2 electron, it will be converted to the cation having 2 positive charge and 2 electrons will be there. So this is the cation. If it is surrounded by ammonia molecules, you can call them ammonia solvated cation. And the 2 electrons per metal that we are getting, they are also surrounded by this solvent molecule. So in this case, solvent is ammonia. So it is ammonia solvated electrons. Okay. The solution is electrically conductive because of these electrons that are removed from the metal atom. So it is conductive, it is reductive, and it is paramagnetic. It is paramagnetic because of these electrons that are removed from metal. So they are in unpaired state, and that is why you can say that they are having paramagnetic nature. Since these solvated electrons get absorbed in the visible region, the color of the solution turns blue. Now the same observation we have also seen for alkali metals. There also we have seen that the color of these solution, that is the metals in liquid ammonia, the colors of the solution is blue, and that is it falls visible region. Now look at the equation. Here we have this metal, it may be any group 2 metals, and there is X plus Y, this is the total number of ammonia molecules. Now out of this X plus Y, suppose X number of ammonia molecules, there it is that is this way ammonia molecules are surrounding the metal, and overall charge is 2 plus. It is still 2 plus because the metal has lost 2 electrons, and the 2 electrons that are lost, each electron is surrounded by Y number of ammonia molecules. So both sides, if you compare in this equation, left hand side, right hand side, total number of ammonia molecules, that is actually same. And here you can see 2 is written outside. That means total Y number of ammonia molecules surrounding each electron, and there is 2 electron we will get in this condition for each metal because it is losing 2 electron. So total negative charge will be 2 negative. So 2 negative, 2 positive, ultimately it is neutral. But remember, because of this electron, unpaired electron is paramagnetic. There is reducing capacity for this solution because of the same reason, because of this electron. And there is also conducting nature. Okay. Concentrated solution is bronze color. Again, the same observation. In case of alkali metals also we have seen, when it reaches a particular concentration range, then the color is changing from blue to bronze color. And when such a solution is evaporated, now what happens? Hexaammoniate means this type of molecule, where 6 ammonia molecules surrounding this metal. So this will be formed. Now, once the solution is evaporated, this MnH3(6), there is slow decomposition of this molecule, and once it is decomposed, there will be formation of MnH2(2). So this is basically amide, because if you just focus on this part, NH2, it is carrying single negative charge. That means for metal, as it is carrying 2 positive charge, so we need 2 NH2 minus anion, which we call amide. So this molecule is basically metal amide. Fine. And there is also formation of ammonia and hydrogen gas. So this is the ultimate fate if we evaporate the solution. So this is the that is the 2 chemical properties for group 2 elements. So now we will switch to application part, that is uses of alkaline earth metals. We will start from the first metal, which is beryllium. Now beryllium, because of its low atomic number, that means the first element is hydrogen, then lithium, then beryllium. So in this way, that is atomic number 1, then helium I have missed. Atomic number 1, then 2, then 3, then 4. So this is beryllium. So here we have very low atomic number compared to other metals. Obviously, it is the lowest atomic number. It is the first element. Here for beryllium, there is low absorption for X-rays. Actually, it is directly related to how many number of electrons are present. So as it is low atomic number, that is proton number 4, and we know that proton number, electron number both are actually same. So electrons are also very low. Per beryllium, it is total 4 electrons. So when there is low number of electron, there will be low absorption for X-rays, and that is the reason that it is basically used for radiation windows for X-ray tubes and X-ray detector. And the reason is this statement, that it has very low absorption for X-ray. So when we are using X-ray for some other purpose, now beryllium is used for the X-ray tube and windows. Now the X-ray tube and windows through which the X-ray will pass, if it is interacting with X-ray, then our purpose will not be served. So we want the X-ray tube or the detector or the radiation windows through which the X-ray will pass, that should not have much interaction with beryllium. Now that is, it should not have much interaction with the material from which we have made these detectors. So detectors, X-ray tube, these should be made of such a material which is having very low interaction with X, and that is possible with beryllium. Why it is possible with beryllium? Because of its low atomic number. Now you can think, then why not lithium? Because it is even lower. It is 3 electron. Beryllium is 4 electron. Then why not lithium? Why not hydrogen? Actually, hydrogen, helium, these are too low. They are gaseous in nature. It is difficult to handle. So let's forget about them. But why not lithium? The reason is lithium is very reactive. Compared to beryllium, it is reactive. So though it is low atomic number, but we cannot use it for this purpose because of its reactive nature. So beryllium is very ideal because it is not so reactive like lithium, and also the number of electrons low, and that is why there is low absorption for X-rays. So that is the reason it is used for this purpose. This is the most important application for beryllium. Then as a moderator in nuclear reactor, there are different types of moderator used in nuclear reactions. Nuclear reactions are actually very, that is the intensity of this reaction, it is very vigorous. So some moderation, that is some materials are used or which will help to decrease this vigorousness. Okay, so beryllium is one such moderator. Since beryllium is transparent to energetic particles, transparent to energetic particles means it has not much interaction with energetic particles. Okay, so that is the reason it is used for to build the beam pipe in accelerator. So beam pipe accelerator, it is basically a pipe through which high energy particles are passed in different instrument. Okay, which instrument, that's not important. Important point is what is the purpose of beam pipe. Through beam pipe there is high energy particles moving, and there should not be any other substance which can interact with these particles, because otherwise the purpose will not be served. So beryllium, as it is having not much interaction with energetic particles because of its low atomic number. So that is why we are saying that beryllium is transparent to high energetic particles. So that is why for to build the beam pipe, we use beryllium metal, because of the same reason that we use beryllium for making the windows for X-ray or the ray tube or detector. Okay, the same reason here also. So these are the applications of beryllium. Next metal is magnesium. Magnesium is used in the removal of sulfur from iron and steel. So kind of purification. Then it is used in the refining of titanium in the Kroll process. So Kroll process is basically that is any titanium ore. From this we extract titanium. That is actually the Kroll process where magnesium is used. It is used also as a photo engraved plate in printing industry. Then alloy of magnesium and aluminium, these two metals together, used as structural material in aircraft and missile construction. The next application is magnesium in powder form or in ribbon form. Ribbon form is, it is like a tape type of structure, okay? Ribbon or tape, whatever. And it can also be in the powder form. So magnesium in these two forms can be used as flash powder. Flash powder, there is a used in fireworks mainly, bulbs, then incendiary bombs and signals. Okay, so these are some special types of bombs which are used for as a weapon, you can say. Then magnesium ribbon is used in the synthesis of Grignard reagent in organic synthesis. Now this application you will see in any organic unit where Grignard reagents are made. So Grignard reagents general formula is RMgX. So what is R? What is X? So when you take any alkali halide, suppose I have taken CH3Cl and then you are treating it with Mg, there will be formation of CH3MgCl. So in general, we are writing it in this way, where R is the alkyl group, Mg, that is the metal, and then we have any halogen. So this is Grignard reagent. It is very important reagent in organic chemistry. Then magnesium is used as sacrificial anode in controlling galvanic corrosion. Now details of this role of sacrificial anode in galvanic corrosion that you will get in electrochemistry chapter. Okay. So these are the applications of magnesium. Next element is calcium. It is used as a reducing agent in metallurgy of uranium, zirconium, thorium. So for the extraction of these metals, there is a separate unit also for metallurgy. So for extraction of these metals, sometimes there is requirement of reducing agent. So carbon is also used as reducing agent, but in this case, we are discussing calcium. So calcium is also one of the reducing agent which is used. It has application in metallurgy. Then we can use it as deoxidizer, desulfurizer, or decarbonizer. So whenever we add the term D before any term, so it is basically the reverse. That deoxidizer means it will, that is oxidizer means which is oxidized. But when I am writing D just before oxidizer, then it means the opposite. Okay, so it is deoxidizer, desulfurizer, decarbonizer for different ferrous and non-ferrous alloys. In the preparation of cement and mortar to be used in the construction purpose, then getter in vacuum tube and in dehydrating oils. These are actually technical terms. This will not go into the details. But why we need to know this? Because you can get question regarding this. Okay. Fertilizer, concrete, plaster of Paris. Now there is one topic in this chapter, that is important compounds of calcium. There also we will discuss separately some important compounds of calcium like gypsum, plaster of Paris. So then you can see the details of this. But now it is just saying that calcium is used in this in the preparation of all these substances. Okay. Then calcium 2+, and it has biological importance also. It is essential for healthy growth of bones and teeth. Next element, this is calcium, this is strontium. So 90 strontium. So these are actually with different mass because of difference in the neutron. I mean to say different isotopes of the same element. So different isotope means while atomic number is same, but because of different neutron number, the mass number becomes different. So mass is expressed by A. So it is equal to proton number and neutron number. P is fixed, but because of difference in N, mass is changed. So this is the definition of isotope. So there are different isotopes for strontium. 90 strontium is used in cancer therapy. Then this ratio of 87 SR and that is two isotopes, different isotopes of strontium, this ratio commonly used in marine investigation as well as in teeth, tracking animal migration, or in criminal forensic. So this ratio is important. Then radioactive tracer in determining the source of ancient archaeological materials such as timber coins. Basically, it helps to identify how old these archaeological materials such as coins, timbers. Okay. Then we have barium. It is used again in metallurgy just like calcium. Its compounds used in different methods. Then deoxidizer in copper refining just like calcium. Its alloy with nickel readily emits electron, hence used in electron tubes and in spark plug electrodes. Then it has application as a scavenger to remove large traces of oxygen. So it can react with oxygen. As a result, the oxygen will be removed. Scavenger. Okay. Other gases also. Now, in some cases, it is required to remove the oxygen and other gases. Other gases such as in television and other electronic tubes. Then isotope, a specific isotope of barium, which is 133. It is used as a source in the calibration of gamma ray detector in nuclear chemistry. So remember, it is 133 barium. Then barium sulfate, that is BaSO4. It has application in medicine as barium meal for intestinal X-ray. So because when this intestinal X-ray is done, just before the X-ray, some barium sulfate we take, that is inside it is taken. Now what happens when it is taken in, it is present inside our body through the intestine because of the presence of BaSO4. And when the X-ray is passed, we can actually see what are the inside of the organs. If there is some problems or some disease is present, that we can easily identify, because as before the X-ray, it was given to the patient so that there is some white marks we can observe once the X-ray is passed. Because if this barium sulfate is not taken, the X-ray will simply pass. We will not be able to see anything, whatever problem is present inside our body. But if this barium is taken, which is known as barium meal, it is a medical term actually. So it helps to identify whether there is any abnormality present inside. Okay. Radium is used in self-luminous paints for watches, nuclear panel, aircraft switches, clock, instrumental dials. So it has some self-luminous property. So if there is dark and you have radium, so it glows. Okay. Then radium is used. This is very important application, radiotherapy for cancer treatment. Okay. Now we have seen all the uses of different elements. Based on this, we have this problem here. In list 1, we have 4 elements. See, all are from group 2. And in list 2, we have starting from 1 up to 5, total 5 applications. We have to choose the appropriate answer from the options given below. Now, the very easy to understand is this one. See, we have seen it has very important application in making windows of X-ray or the tube or the X-ray detector. So obviously A will be matching with 4. Now A is 4, that you can find in these 2 options. So you can easily cancel these 2. Now once it is so, next we can say magnesium. Remember, incendiary bombs and signals, these applications we have seen. That means B should be matching with 3, which is present in option 2. Then calcium, it is used in extraction of metals. Even if you cannot remember that magnesium is used in bombs and signals, it is true that out of these 4, in extraction of metals, we use calcium, not beryllium, Mg or Ra. So that is also the indication. And obviously, Ra, it is used in the treatment of cancer. Remember, we have seen in the last point that radium is used here in the treatment of cancer. Strontium also written 90 which is used in cancer therapy, but remember strontium is not present in the options. So even if we have doubt whether B is used in bombs and signals, but remember these are very specific, that radium is used for cancer treatment. It is not B, Mg or Ca, it is only radium because Sr is not present, right? So D should be matching with 1. So if you are just sure about that A is matching with 4 and D is matching with 1, then also it is enough to answer that option 2 is the correct option. Fine. That is just by eliminating other options. Again, if you have already solved this question, it is not anything new. It is asking that metal used for making X-ray tube. Now only this is possible. Here the 4 options that are given, this is from group 2, this is group 1, this sodium, this is again 2, this is again 2. But X-ray tube window or X-ray detector, that is made only from beryllium. Sodium is obviously not possible, it is too reactive, you cannot make anything. Now magnesium, calcium, they have very high atomic number, that is also not possible. Only Be, because it is very transparent to X-ray. What I am trying to say by transparent is that it has less interaction with X-ray. So that is why you can use for preparation of X-ray tube window or X-ray detector. So beryllium should be the correct answer. So once we have finished the application part, next there is specific compounds. The same thing we have also seen in case of group 1 metals. So here first there will be oxide, that is the general formula if I write MO. Then there will be hydroxide, general formula is MOH whole 2. Then hydride, general formula MH2. What about halogen? That is halide, it should be MX2. Okay, so these one by one we will discuss: oxides, hydroxides, hydrides, halides. Now before going to the discussion, if we simply compare with group 1, here we have di-positive ion, unlike group 1 where we have seen monopositive ion, Na+, K+. So in this case, it is the difference that only common oxidation state for group 2 is 2+. Because of increased nuclear charge and smaller size compared to group 1, these metals, they form compounds with less ionic nature. So if you compare, suppose you have taken any halide, I am talking about suppose NaCl, and in the same period there is magnesium, so it is MgCl2. Now here anion is fixed, anion is common, both are chloride, but see the metal is, in case of sodium, it is having +1 charge, but here it is +2 charge. Now when charge is high, increased nuclear charge, and also the size is small. We know when you move from Na to Mg, that is you are moving from left hand side to right hand side in the periodic table, there is decrease in size. So because of these two reasons, smaller size and nuclear charge, that means charge density is now high. I have written mentioned what is charge density several times. It is basically charge divided by volume. So when charge is high and size is also small, that means volume is small, so this charge by volume ratio, obviously this will increase because the denominator is decreasing, numerator is high compared to alkali metals. So because of this increased charge density, now the ionic character is less, which is according to Fezan's rule. When charge density is very high, covalent character increases. So this is the reason why they are less ionic than the corresponding compounds of alkali metals. Now don't compare NaCl with magnesium oxide or hydroxide. It is better you compare within the same. So that is what is mentioned corresponding compound. That is, I have taken here chloride for both the metals. Okay, so that comparison can be done easily. So anion is fixed. Now you can compare. If you have taken different anions, then comparison is not. Okay. When you are comparing two things, obviously the other factors you have to make fixed. So here chloride is fixed. Only we have changed the metal. So metal size is less, charge is high, charge density high, covalent character high. Fine. So this is the difference with the compounds of alkali metals. Now we will actually see the characteristics of oxides of alkaline earth metals. Monooxides of alkaline earth metals. So unlike group 1, where we have seen different types of oxides are possible, peroxide, superoxide. So here monooxide is formed by all these elements. How we can obtain? Either by heating the metal in oxygen. So this part you have already seen when we have discussed the chemical properties. Remember, in chemical properties we have seen how these metals, they react with air, and in air there is both O2 and N2, nitrogen and oxygen. So there we have already seen it. So again it is mentioned here that you can make the this is the general formula for the oxide, directly heating the metal in oxygen, or so this is the method. But this is not the only method. You can also do some thermal decomposition of their carbonate. So see, this is the carbonate MCO3. General formula MCO3 because carbonate is having 2 negative charge and metal is 2 positive charge. So the formula is MCO3. So when we are heating it, there is formation of oxide along with CO2 gas. And this metal is basically starting from beryllium up to barium. Enthalpy, okay, let me write all the oxides so that it will be easier for you. First oxide BeO, then MgO, calcium oxide, SR oxide, B oxide. The enthalpy of formation of these oxides is quite high, and that is the reason they are very stable. Because if you want to know their thermal stability, obviously you have to consider the enthalpy of formation value. Enthalpy of formation means the energy which is released when you are making 1 mole of any compound from its constituent elements under their normal state. Normal state means if you are preparing something, suppose you are preparing something from carbon as element. So carbon under normal condition, we know it is solid form. It is not gaseous or liquid, right? So when you are making something from carbon, it must be in the solid state. That is a normal state. So this is the definition of enthalpy of formation. So when it is very high, Mostly it is negative value, that is energy is released, so that is why it is negative. When it is high, that means they are very stable. They have high melting point, very low vapor pressure, very good conductor of heat, and are chemically inert. So you can deal with these oxides easily. They are not very reactive. So see, this is one important difference with the oxides of alkali metals. Oxides of alkali metals, they are comparatively much reactive, not like this. So these are the characteristics of these oxides of alkaline earth metals. Fine. Some more characteristics. The first two oxides, that is beryllium oxide and magnesium oxide, almost insoluble in water. Whereas the other oxides, they can form hydroxides when they are soluble in water. Let me write it again. So out of these two, water solubility is not present, but these three can, that is easily soluble in water, and they can form the hydroxide. Hydroxide means MOH whole 2, where M is CaSR or Ba. The first two are basically covalent, so that is why insoluble in water, but the others are ionic. Now, what about their basicity or acidity? Actually, not, we cannot say acidity because they are not non-metals. When you have oxides of non-metals, then you can talk about acidity, but they are metals. Now, as we know, down the group, metallic character is increasing. So when you are moving from beryllium to magnesium, then magnesium to calcium, gradually metallic character is high. Now, BeO, obviously it is more metallic than BeU. So BeO is amphoteric in nature. Then magnesium oxide, it is basic, but it is weakly basic. Then the rest of the three, they are strongly basic because now you have moved down the group. So these three, you can say strong basic character. Because metallic property when increases, basicity also increases for the corresponding oxide. And as they are thermally stable, we have seen in the previous slide the characteristic, chemically inert, and they can withstand high temperature. So as they are resistant to high temperature, they can withstand it. So that is the reason they are used for lining furnaces and hence in refractory materials. Because for this, in these cases, high temperature resistant material is required. And this is important application of these oxides. Except the first element, the remaining metals, that is their corresponding oxide, it can form peroxide also. And how we can prepare it? It is prepared by heating the monoxide. So we have taken this monoxide MO, but see here M is any of these four. B is not there. So when you are treating it with oxygen, we are getting peroxide. So peroxide we are basically here preparing in a special way. In case of group 1, that is alkali metals, we have seen that for sodium, peroxide is the main oxide that is formed when sodium is reacting with oxygen, right? But in group 2 elements, basically when they are reacting with oxygen, there is formation of the general formula MO. But see, special case we can, that is special, sorry, it is not BA, it is M, where M is any of these. It is prepared by heating monoxide. So first you take the monoxide, then you treat again with oxygen. Now the formula is different, it is MO2. Now that is expected. Why I am saying so? Because when it is +2 and -2, normal oxide, that means oxygen carrying single 2 negative charge. But when it is peroxide, 2 oxygen, 2 negative charge. So O2 is basically carrying 2 negative charge, right? This is O2 carrying 2 negative charge. So to nullify that, that is to balance it, we need 2 plus. So that is why the formula for peroxide and oxide is different, MO and MO2. These peroxides are used as commercially as oxygen source because it is peroxide. So we can, when it will decompose, we can get oxygen. So as if it is a source of oxygen, or you can say it is behaving as oxidizer. Okay. So related to oxide, here we have a problem, but if you look carefully in this problem, only these two oxides are group 2 oxides. K2O is group 1 oxide. Nickel oxide, it is basically from D block. And we have cesium oxide. But this is also from group 1. This is group 2. This is group 2. Now look at the formula. And all these are basically having O2 negative ion. Why? Which is clear from the formula, because for Mg and Sr it is the formula is MO, right? When you have group 2, formula is MO. But when with oxide it is group 1, the formula should be M2O, because now the metal is having only single positive charge. So to balance this O2 negative charge, we need 2 potassium or 2 cesium. Okay, so these two are group 1. So under M2O we have K2O, we have CH2, and under MO we have MgO and SRO. Now we have to find the correct order, that is increasing order, for their basic character. Now basic character, when we want to know, it is basically related directly to the metallic character. So metallic character of M. So once if you know the metallic character, that is which metal is more electropositive, then you can easily find the order, right? Now if we write their position, so see, this is group 1, this is group 2. Here just beside sodium we have Mg, which is group period 3. Below sodium we have potassium, and here we have calcium. Now the position of cesium: sodium, potassium, rubidium, cesium. Here we have Sr, and nickel is basically D block, so it will be in the third period, obviously. Sorry, fourth period, obviously. So I am writing simply it is somewhere here. Which period, that is also not important. It is from D block, so its metallic character, that is electropositive character, it will be lesser than S block. So this is S block, this is D block. So D block metallic, it is true they are metal, but their metallic character is always less. So nickel oxide, that should be having lowest basicity. Now this much information, isn't it enough to choose the correct option? It seems as if option C should be correct, because only in option C, at the last point, that is in the lowest side, we have nickel oxide, nickel 2 oxide, oxidation state 2. But why, what about the others? If you look at now S block only, forget about nickel. So sodium is, sorry, we do not have sodium. Magnesium, it is here, but compared to magnesium, we know when we move down the group, the electropositive, that is a metallic character, is high. So obviously strontium will have more basic character, that is a strontium oxide that will have more basic character compared to Mg, because it is below Mg. Similarly, if you compare cesium and potassium, the basicity character from the CH2O, it should be higher than potassium. So CS should be before potassium, Sr should be before Mg. Now see, CS before K2O, that you can find here, right? And Mg lesser than Sr, that you can find here. So keeping all these points together, it seems as if option 2 should be right. Okay. Now it is true that when you are moving down, we have just compared these two, and we have compared these two. So this is enough to understand which option is correct. So it should be option C. So here I am just writing maximum metallic character CS, then K, then Sr, then Mg, and at last we have this D block element, which is nickel. So just add oxygen, you will get the correct option. But here just one hint I would like to give, though it may not, it is for this case it may not be always. If you know this much information that D block metals, it is lowest reactivity compared to S block, then also you can choose option C, because only in option C nickel oxide is at the last. So you can just apply this trick if you are running out of time. But actual explanation is that strontium is more reactive than Mg, so strontium oxide will be more basic. So just focus on any particular group. Here this is the order. Then focus on group 1, this is the order. So in this way, comparing all these points together, we have to choose option C, increase in basic character. Next is hydroxides. So hydroxide general formula. When alkaline earth metals or their oxides, remember except beryllium oxide, they are treated with water, you can get hydroxides. So the first equation, we are treating metal directly with oxygen, we are getting hydroxide and hydrogen gas. In the second equation, we have taken the oxides of the metals, then we are treating it with oxygen, and we are getting MOH whole 2. The reaction of this oxide with water, there is a specific term we use, which is slacking. Fine. The first two hydroxide, that is hydroxide of beryllium and magnesium, they are insoluble. Fine. So how we can obtain it? We can also obtain, because of this insoluble character, we can also get these two hydroxide in a different way also. So which reaction we are doing here? From suitable metal salt solution by precipitation with HO minus. So they are having some insoluble character. Now if you are doing the reaction, that is if you are producing MgOH whole 2 and BOH whole 2 in water, because of their insoluble character, you can get them in the precipitate form. So we are just utilizing that fact. We are making BOH whole 2 in the precipitate form, MgOH whole 2 in the precipitate form. So we have started the source of beryllium, we have taken BeCl2, chloride of beryllium. Then some hydroxide source that we need, because ultimately we are preparing hydroxide of B. We have taken sodium hydroxide. So we are getting BOH whole 2 and NaCl. NaCl is highly soluble in water, but BOH whole 2, because of its insoluble character, we will get it in the precipitate form. And it will also help us to ultimately purify the product. You can filter it and easily separate the product from the reaction mixture. In the second case, we have taken sulfate salt of magnesium as the magnesium source, and NaOH as usual. Again, we are getting the magnesium hydroxide. But you cannot use this equation for the other hydroxide because they are soluble. So we are just utilizing that is exploiting this fact that these two hydroxides are insoluble. The next point is very important. Hydroxide, that is the MOH whole 2, its solubility, thermal stability, basic character increases down the group. So all these 3 points. So why this is important? Because problems based on this order, down how it is changing down the group, this is very common pattern of question. So this information is important. So whether it is solubility, thermal stability, basic character, everything is increasing down the group. Fine. And there is smooth increase, so there is no discrepancy. Alkaline earth metal oxides are, however, less basic, less stable than alkali metal hydroxides, and that is again expected because of their higher ionization enthalpy. There means group 2 elements, their ionization enthalpies are higher compared to group 1. Then they are also having smaller ionic size, greater lattice energies. So these are the reasons that why they are less basic and less stable compared to metal hydroxide. Okay. Beryllium hydroxide is amphoteric in nature. So remember, down the group, basicity of the in case of oxides we have seen basicity is increasing. So in case of hydroxide also, you can expect the same thing, because down the group metallic character increases, and when metallic character increases, the hydroxide salt also, it will show more basic character. Beryllium hydroxide, it is amphoteric in nature. That means it can react both with acid and alkali, which is clear from this equation. The first equation, it is reacting with sodium hydroxide, producing Na2BeO2 and water. In the second case, it is reacting with hydrochloric acid, producing chloride salt. So if you are thinking about the that is charge, it is Na2. That means we have two Na plus ions here, and BeO2, it is basically carrying two negative charge, because beryllium is 2 plus oxidation state, and 2O2 means 2 oxide ion. So total negative charge 4 minus. So 2 plus 4 minus 2 negative charge extra outside the third bracket, which is balanced by 2 sodium. So in this way, you can understand why the formula is like this. So BeOH whole 2, it can react with acid as well as alkali, which is clear from these two equations. Fine. Some more points related to hydroxide. Low ionization enthalpy. It is true that compared to alkali metals, their ionization enthalpy is high, but actually they are S-block metals. So if you compare with other elements in the periodic table, obviously ionization enthalpy is very low. Here, because of this reason, the metal oxygen bond in MOH, there is basically 2OH. But this bond energy, MO bond, it is weak, breaks to give HO minus ion in solution, and that is the reason why we are having basic character. And it is also true for alkali metals, the same reason. On moving down the group, this ionic size, that is the metal ion size, though this type of bond, literally we should not write, because it is ionic bond, and when there is ionic bond, it is basically metal 2 plus and 2 HO minus. It is not that there is any electron sharing occurring. So better you can also consider in this. It is basically just interaction between metal 2 plus and HO minus. That's it. So when we are moving down the group, the size of this M2 plus is high, and also down the group BE, you are moving up to BA. So down the group, not just size is high, but also ionization enthalpy decreases. So because of this reason, as the size of this M2 plus is high, the distance between M and oxygen bond, that is also high. So you can easily break it. As a result, MO bond becomes weaker when weaker down the group, and hence basic character also increases down the group. Right? You can easily get HO minus ion. That is the reason. Compared to alkali metal hydroxide like NaOH, KOH, now the hydroxides of alkaline earth metals, it is true they are having some solubility, but less soluble in water compared to the hydroxides of alkali metals. And within the group, that is down the group, the solubility increases. Now this information we have already seen in the previous slide, that is solubility, thermal stability, everything there is smooth increase down the group. That is this point, the third point. Okay. Now look at the last statement, what it is saying. Lattice enthalpy, hydration enthalpy. So remember, whenever we want to know whether a particular compound is soluble in water or not, we have to consider enthalpy of solution. Now this is basically the combined effect of lattice enthalpy, I'm writing L here, and hydration energy, del H hydration. So when del H hydration is basically mostly negative, so more negative this hydration becomes, because this is always positive. So more negative is Delitzsch hydration. That means Delitzsch solution, there is a chance it will also be negative. Now when this is negative, then only water solubility is possible. If it is positive, that is Delitzsch solution, enthalpy of solution, then water solubility not possible. So what we will expect? We will expect that less lattice enthalpy and high hydration enthalpy. Then only Delitzsch solution will be negative, right? So read the statement is saying that both lattice enthalpy and hydration enthalpy decreases down the group. That is, individually if you consider lattice enthalpy and hydration enthalpy, both are basically decreasing down the group as the size of cation increases, because when there is increase in size, not just cation, anion also, lattice enthalpy it is inversely related. So when size is high, lattice enthalpy decreases, and down the group, that is the reason lattice enthalpy decreases. And cation size increase means hydration enthalpy is also increasing down the group, because when size is small for the metal, like Be2 plus, charge density is very high. That is same amount of charge now in close volume. I mean to say in less volume. But down the group, the charge density is very less. So hydration enthalpy is less. So lattice enthalpy, hydration enthalpy, both are decreasing down the group as the size of the cation increases. But lattice enthalpy decreases more rapidly compared to the decrease of hydration enthalpy. And that is the reason that the overall effect is such that down the group, Delitzsch solution becoming more and more negative, because the rate at which lattice enthalpy is decreasing, it is very rapid decrease. And that we want, because when Delitzsch lattice is less, then Delitzsch solution, the chance that Delitzsch solution will be negative, that is high. So the rate at which lattice enthalpy is decreasing and the rate at which hydration enthalpy is decreasing, these two rates are not the same. Lattice enthalpy decreasing more rapidly compared to hydration enthalpy decrease. And that is the reason overall Delitzsch solution becoming negative, more negative and negative down the group. And that is the reason the solubility increases down the group. So solubility increase or decrease, that is simply observation. But what is the reason behind that? How we will explain that? That may be different. Suppose in two different cases, in both cases, suppose down the group, I am saying solubility is increasing. But it doesn't mean that the reason behind it will always be same. Reason may be different. And why the reasons are important for us to know, because sometimes you will get question where it will be mentioned directly in the question that what is the explanation there for which down the group there is increase in solubility or decrease in solubility. So that is why it is important as for to know what is the actual reason for which the solubility is increasing down the group. Fine. So after hydroxides, next we have hydrides of alkaline earth metal. So general formula MH2. Hydrides of these alkaline earth metals, that is heavier alkaline earth metals means down the group, the metals that are you can consider strontium, barium. So heavier alkaline earth metals, their hydrides are basically ionic. But the first hydride BH2, it is not ionic, it has polymeric structure. So which reflects basically covalent character, because for ionic compound what you expect? You expect crystal structure. But when there is polymeric structure, obviously it is not ionic. So down the group ionic nature increases, and the first hydride, first element's hydride BH2, it has polymeric structure, which proves its covalent character. B and Mg it form covalent hydrides, that is BH2 covalent, MgH2 covalent, where each H atom is connected to two metal atoms. Okay, Mg per Mg 2H, because oxidation state is 2 plus, and hydride means H negative. So this is the structure of BeH2. It has a special kind of bonding. Now you may be thinking that why it is having polymeric structure. Now the reason is, by forming this type of structure, they can, that is some amount of electron deficiency can be, they can make up. Because see, here if you consider how many electrons are present between, because H normal, under normal condition we cannot have H, it is having bond both sides, that is not possible, right? But here what is happening, we are calling it 3 center 2 electron bond. So total center in this bond, that is the pink highlighted area, total number of centers obviously 3, so that is why it is 3 center. And total number of electrons is basically 2 electron. So don't write in this way as if 2 electron here, 2 electron here. No, it is not that. It is completely wrong. Let me erase it. So it is not right way to draw the structure. So 3 center, and there is basically total 2 electrons. And these 2 electrons as if it is hovering all over this region. So that is why we are calling it 3 centered 2 electron bond. In this way, here also 3 centered 2 electron. Here also 3 centered 2 electron. Okay. So when this type of polymeric structure is there, if you consider the monomer like this, how many electrons are there? Normal covalent bond, total 4 electrons surrounding beryllium. But if you have this type of polymeric structure, now just focus on a single beryllium. Now surrounding beryllium, there are total 8 electrons. So as if octet is complete. So this is the reason they form, to remove their electron deficiency, they can form this type of special kind of bond, which is 3 center 2 electron bond. Because when we are talking about normal bond, suppose I am writing bond between A and B, covalent bond. So what we know, 2 center 2 electron, that is the normal case. But sometimes you will see in some compounds, also you can see 3 center 2 electron bond in some other p block elements, not only this. So this is 3 center 2 electrons. So 2 electrons will be over 3 center. So that is why we have this type of name. So BH2 is polymeric, having polymeric structure, and it is covalent in nature. This is an example of molecule with 3 centers sharing only 2 electrons, and it is called, because of this particular shape, it is called banana bond, because it has similarity with the shape of banana. Hydrides of alkaline earth metals, they react with water, they liberate hydrogen gas. So this is the general equation. M is Be to Ba. When hydride is reacting with water, we are getting the hydroxide and H2. So hydride of alkaline earth metals react with water to liberate hydrogen gas, and hence they can act as reducing agent. So these are the informations regarding to hydrides. Next day we will also finish the halides, and then we will have the other compounds like sulfate, carbonate, etc. So we are ending the session here. Thank you for listening.